Today you're going to learn the last section, 3.7, how to graph absolute value functions and how to translate them. So, what are we doing? Well, we're going to translate graphs of absolute value functions. But before we translate them, let's learn what they are. So an absolute value function is a function that contains an absolute value expression. So here's your first piece of information. Look at this. The parent absolute value function is this. So f of x equals the absolute value of x is the parent function of an absolute value function. So the graph of f of x equals the absolute value of x is v-shaped. You'll notice right here, it's v-shaped and is symmetric about the y-axis. The vertex is the point where the graph changes directions. Make note of that. The vertex is the graph or the point at which the graph changes directions. And the vertex of the parent function is 0, 0. The domain, notice domain, x value. It goes right, it goes left, so it's all real numbers. The range is anything above 0. So you'll notice the y value is greater than or equal to 0. Now, this is the important part regarding transformations. The graphs of all other absolute value functions are transformations of the graph of the parent function. The transformations that you did in 3.6 are also exactly the same as in this section. So for example, f of x equals, like let's say we had the absolute value of x minus 2. This means that the graph will be shifted or translated 2 units to the right. It's the same process as last section. So example number 1, graphing each of these values. Now you'll notice right here, plus k. That means the vertical change. And minus h, that's going to be the horizontal change. So let's start with our first a. We're going to graph the function, and then we're going to compare each graph to our parent function, and then we're going to describe the domain and range. So we have to graph the function g of x equals the absolute value of x plus 3. We're going to make a t-table. Now, here's the t-table, or here's the problem that we have. Whoops, it should not be y, it should be g of x. The t-table, some people start picking values, and then they get a line because they don't know where the vertex is. Now, the vertex in this problem starts at 0, 0. Well, what happens to it? It goes down 3 units. So the vertex is going to be 0, 3. So if you pick, for example, 0, and plug it in here, you're going to get 0, 3. So I know that 0, 3 will be my vertice, or my vertex, since this entire graph has been shifted up 3 units. Now I'm going to pick values that are bigger than 0 and less than 0. That way I can get both sides of my symmetric graph. So if I plug these all in, this is going to be 2, 5, 1, 4. Let's see, that'd be negative 1, 4, and 2, 5. So if I graph these, that would be what your function looks like. So what's my x value? Well, my x value can be anything. So my domain is what? The domain is all real numbers. Now my range, though, is your vertice. Your vertex has gone up 3. You'll notice right here, it can't be anything underneath 3. So my range is anything that is greater than or equal to 3. So y is greater than or equal to 3. But now we need to compare and graph. What's happened? We can say that the graph of g is translated 3 units up from the graph of f, since it's gone up. Now we're going to do the same thing for part B. So part B, you'll see that now it's happening, the translation is happening to your x. So how many units is this going to be translated? Well, it should be translated 2 units right. So if it's 2 units right, that means my new vertex is going to be at 2, 0. And if you don't know that, all we have to do is plug in values. So if I plugged in 2, the absolute value of 2 minus 2 is 0. So if I pick values that are smaller than that and greater than that, you would get symmetric numbers. So let's see, 1 minus 2, that's going to give me the absolute value of negative 1, the absolute value of negative 2, the absolute value of 1, and the absolute value of 2. So if I graph that, that's what I get. I get a graph that's been translated 2 units to the right. And here we go. We know the domain is all real numbers. The range is bigger than 0. Here's 0, so it's bigger than 0, or equal to 0. And the graph of M is a translation, or is translated, 2 units right of the graph of F. In example 2, we're going to stretch, shrink, and reflect. Stretching is going to be, and shrinking from the value of A. Now reflecting is if you make it a negative. So we're going to graph and compare and write the domain and range. So you'll notice that this has not been translated right or left, so the vertex is still going to be at 0, 0. So if I graph them, I'm just going to make a table of values. Notice I'm always making 5 table of values. I always find the vertex first. I always find the vertex first. And then I pick numbers that are smaller than the vertex and bigger than the vertex. The reason I do this is so I can get a symmetric graph and graph points to make an accurate graph. So if I plug this in, this is going to give me 2 and 4, and this would also give me 2 and 4. If I graph them, you'll notice that it got steeper, which means it's been stretched vertically. So this is something that you have done and learned already from the last section. The function q is in this form where a is 2. So that means it is a vertical stretch of the graph by a factor of 2. The domain is all real numbers and the range is y is greater than or equal to 0. Now part B, same thing, but you'll notice it's now negative 1/2. It has not been translated right or left, so 0 would be our vertex, 0, 0. And if you plug in values, this would give you negative 1/2. That would not be what you got. Hold on, let me erase that. 0, 0. And if I pick negative 1, that's going to give you negative 1/2. Negative 2 is going to give you negative 1. 1 would also give you negative 1/2. And 2 would give you negative 1. If we graph these values, you'll notice that it's been reflected and it's gotten what? It has been vertically shrunk. We've smushed it in. It's been smushed in. So what does that mean? That means that the function p is in the form negative a times f of x, and a is 1/2. So that means p is a vertical shrink by a factor of 1/2 and a reflection in the x-axis. It's been reflected in the x-axis. The domain is all real numbers, but now y has to be less than or equal to 0. Notice all values of y are less than or equal to 0. All right, so now we're in vertex form. Vertex form of an absolute value equation. You need to know this, you need to memorize this, and you need to understand what these parts mean. The absolute value function written in the form g of x equals a multiplied by x minus h plus k. Now, I'm going to make note of this right now. Notice that it's x minus h. If you are given something like this, you have to undistribute the 3. And that would mean that 3 is being multiplied to all of these values, and then this would move 3 to the left. So it's not 9 to the left, it's 3 to the left. And that would help you with the vertex. So, a cannot be 0. It is in vertex form. The vertex is hk. The vertex is hk. Do not forget that. That'd be something great to remember. The vertex is hk. The vertex is hk. Any absolute value function can be written in the vertex form. So if you take the h and you set it equal to x, so x equals h, that is the graph upon the line of symmetry. So x equals your x value, x equals h. If the vertex is 5, 2, that means the line of symmetry is x equals 5. If it's -3, -9, x equals -3 is your line of symmetry. All right, example 3. We're going to graph these two functions. F of x equals the absolute value of x plus 2 minus 3, and g of x equals the absolute value of 2x plus 2 and then minus 3. Compare the graph of g to the graph of f. So here's what we're going to do first. We're going to graph the first one. Now here's how you find your vertex. This graph, if you notice inside, it's x plus 2. Therefore, it's being shifted 2 to the left, down 3. 2 to the left, down 3. So I'm going to make a t-table. Because 2 left, down 3, -2, -3 is my vertex. So I'm going to pick two numbers bigger than that and two numbers smaller than that. If I plug them in, they should be symmetric. So let's see. 0 plus 2, 2 minus 3 would be -1. If I plug in -1, that's going to give me -2. If I plug in -3, that gives me -2. And if I plug in 4, that gives me -1. So now I'm going to make a t-table for the second value, x and g of x. Now, this is where it gets important. You'll notice right here, this is important. Here it is. Whoop, whoop. Look at that. The function g is not in vertex form because the x variable does not have a coefficient of 1. So we got to factor that out. Let's put this off to the side. If I redid this equation or this function, I would factor out a 2. Undistribute a 2. Now my vertex is, let's see, left 1, down 3. So -1, -3 is my vertex. I'm going to pick two values bigger and two values smaller than -3. And there's my t-table. So I'm now going to graph them. And that would be my two graphs. Notice I've labeled both graphs. The black one represents the graph of g. The red one represents the graph of f. So what's happened? How does one gone to the other? So let's look. If f is my original one, look at the red line. What's happened? Well, it's been shrunk. And how do I know it's been shrunk? Well, because it's been squeezed together. So this is a horizontal shrink. How do I know it's a horizontal shrink and not a vertical stretch? This is why. From last chapter, you noticed that if it's a horizontal shrink or stretch, the y-intercept is the same between the graphs. If it's a vertical shrink or stretch, the x-axis is the same. So this is a horizontal stretch of what? Well, it's a horizontal stretch of, well, if we look at our function, 2, which means it's a factor of 1/2 because it's moving closer to the y-axis. It's been shifted 1 unit to the right as well. So here's what we have. It's been translated 1 unit right, and graph g, function g, has a horizontal shrink by a factor of 1/2. And lastly, combining transformations, putting them all together. So H tells you to go right or left. K tells you to go up or down. A tells you it's being shrunk or stretched or reflected. So here we go. Let G be this function. Describe the transformations from the graph this to this. Well, what does it look like it's happening? We have a negative, we have a 2, we have a 1, and we have a 3. So we have 4 different transformations happening. The first one, is that this graph from the absolute value of x, the parent function, has been translated horizontally 1 unit right. That's how you get this. Then from there, it's being multiplied by 2. And because we're multiplying the outside, that means we're multiplying the y value, so that means it's going to be vertically stretched by a factor of 2. And the reason we know that is because it's being multiplied to the y values. So it's after we've done something to x, we're multiplying it. It's vertically stretched by a factor of 2. That's a review from section 3.6. And then we get this. So what do we have to do now to the 2? We have to reflect in the x-axis. If we reflect in the x-axis, that's how we get this. Remember, the y values change. So that means that's why we're reflecting in the x-axis. And lastly, we have to add 3, which means we have to translate 3 units up. So we have all 4 of these transformations occurring. We now have to graph it. If we graph it, we know it's been translated 1 unit right, 3 units up. My vertex is going to be at 1, 3. So the x values I'm going to choose are going to be, let's see, 1, 3 is the middle. So I'm going to pick 2 values bigger and 2 values smaller. And there would be my graph. Notice that the domain would be all real numbers, and the range would be y is less than or equal to 3.